9 machines, 1 job, cutting through everything the ground can throw at them. From city sewer lines the width of a dinner plate to a highway tunnel wide enough for 4 lanes of traffic. We start small, with a robot no bigger than a washing machine boring utility lines under city streets, and work up through hard rock grippers, shield machines built for soft clay and river mud, and hybrids that switch personality mid-drive. We finish with Bertha, the 57-foot giant that dug Seattle's biggest tunnel and nearly didn't make it out the other side. The Herrenknecht AVN is barely a tunnel-boring machine by size, and that's exactly the point. Engineers built this class to bore utility tunnels for sewer lines, water mains, and cable ducts under city streets, without ever opening a trench. No crew rides inside. An operator steers it from a control container at the surface, watching a laser guide beam on a screen, while the machine itself became the standard for pipe jacking worldwide after it first went to work in the 1970s. An AVN machine can be built as small as 6 inches across, small enough to slip a fiber conduit under a highway without anyone above ever knowing it passed. At the other end of its range, it stretches past 13 feet, still tiny next to the machines coming up later in this episode. Hydraulic jacks at the launch shaft push pipe sections through behind it, applying up to 3,000 kilonewtons of thrust, while the cutterhead grinds forward meter by meter. Because nobody works inside a bore under about 30 inches, these rigs handle ground conditions like collapsing sand and high water tables that would be far too dangerous for a hand-dug tunnel. A typical drive advances just a few meters an hour, slow next to the giants ahead, but fast enough to lay a city block of sewer line in a single overnight shift. Stand a typical AVN unit on end next to a person, and it barely reaches the chest, about 3 feet across on an average residential job, tucked entirely underground where nobody sees it work. The whole cutting module, without the trailing pipe string behind it, runs about 10 feet long. It disappears down a shaft the width of a manhole and does not resurface until the drive finishes, sometimes a quarter-mile away. Robbins built its main beam gripper machine for 1 job, chewing through solid rock without any support from a tunnel lining. Instead of pushing off segments behind it, the machine grips the tunnel walls with steel pads and shoves the cutterhead forward using that grip alone, then releases, repositions, and grips again. The most famous example, nicknamed Big Becky, spent 6 years boring the Niagara Tunnel project starting in 2006, carving a new water diversion route for the Sir Adam Beck Power Station through dolostone, sandstone, and shale beneath the Niagara Gorge. Big Becky's cutterhead measured 47 feet across, 14.5 meters, making it the largest hard rock gripper machine on Earth when it launched. 48 motors turned that face, and 48 disc cutters chewed into rock, rated among the toughest a TBM had faced, delivering over 4,000 kilowatts of cutting power. On a good week, the machine advanced 10 meters a day, gripping, thrusting, and re-gripping in a rhythm that could run around the clock. The geology fought back, though. A fractured water-bearing fault zone slowed the drive to a crawl for months, and added roughly 2 years to the schedule before the machine finally broke through in 2013. Look at the face of the machine, and you're looking at 48 steel discs, each one free to spin on its own axle as it rolls across the rock. They don't cut so much as crush, pressing in with enormous force until the rock fractures ahead of them, chip by chip. Behind that face sit the machine's namesake grippers, 2 curved steel shoes the size of garage doors that press outward into the tunnel walls to hold everything steady during the next stroke. When rock is too broken or too shallow to trust a bare tunnel wall, engineers reach for a single shield machine instead of a gripper rig. A steel cylinder shrouds the entire cutterhead and the crew working behind it, and instead of gripping the walls, hydraulic rams push off a ring of precast concrete segments bolted together just moments earlier. Norway's Follow Line project put 4 Herrenknecht single shield machines to work in 2016, each one boring through hard gneiss beneath Oslo, to build what became, at completion, the longest rail tunnel in Scandinavia. Each Follow Line machine cut a bore 9.96 meters across, wide enough for a double-track high-speed line. 48 thrust cylinders shoved the shield forward against freshly placed rings with up to 50,000 kilonewtons of force, letting the crew build finished tunnel lining and advance at the same time instead of lining it later. On strong days, a single machine advanced 20 meters, and across the full 18-kilometer twin-bore drive, the 4 machines placed tens of thousands of segments without ever leaving the rock exposed for more than a few meters at a stretch. The whole assembly, cutterhead to the back of its trailing gantry, stretched longer than a football field. Tucked inside the tail of the shield sits the segment erector, a vacuum-gripped robotic arm that lifts each curved concrete piece and swings it into place against the ring ahead of it. It works in the dark, bolting 6 or 7 segments into a complete circle before the machine even finishes its next push. That ring becomes the finished tunnel wall. No second lining pass required. A double shield machine tries to have it both ways. Grip the rock like an open gripper machine when conditions allow for speed, then collapse into single shield mode and push off segments when the rock turns unstable. Telescopic shield sections let it switch between the two without stopping. Spain's Guadarrama Tunnel, part of the high-speed rail line from Madrid to Valladolid, used 4 of these machines, starting in 2002, to bore twin bores through granite beneath the Sierra de Guadarrama Mountains, at the time among the longest hard rock rail tunnels drilled anywhere in Europe. Each Guadarrama machine cut a face 9.5 meters across and could switch gripping modes in minutes rather than the hours a crew would need to reconfigure a single-purpose rig. Running in gripper mode through competent granite, the machines advanced up to 30 meters in a single day, genuinely fast for hard rock boring at that diameter. Where fractured zones threatened to collapse before a lining went up, the crew shifted to shielded mode, trading speed for safety while segments went in behind the cutterhead. Over roughly 2 years of tunneling, the 4 machines completed twin 28-kilometer bores, and Guadarrama opened in 2007 as one of the longest rail tunnels on the continent. Set beside a person, the cutterhead alone stands over 3 times human height, a wall of steel discs wide enough to swallow a double-track rail line whole. Behind it, the machine's shield and gantry train stretched roughly 200 meters from cutting face to the last support car, closer to the length of 2 football pitches than anything most people would call a single machine. An earth pressure balance machine solves a problem gripper and open shield rigs can't: how to bore through soft, waterlogged ground without the face collapsing in front of the cutterhead. It keeps the excavated soil itself, packed under pressure inside a sealed chamber, pressing back against the ground ahead, while a screw conveyor bleeds spoil out at a controlled rate. London's Crossrail project, now the Elizabeth Line, used 8 Herrenknecht EPB machines between 2012 and 2015, each one named after a notable woman, Phyllis, Ada, and Elizabeth among them, to bore 42 kilometers of new tunnel through London clay and sand beneath one of the busiest cities on Earth. Each Crossrail machine cut a bore 7.1 meters across, threading new twin tunnels within meters of live underground lines, building foundations, and Victorian sewers without disturbing any of them. The screw conveyor at the base of the cutterhead could hold back groundwater pressure exceeding 3 bar while extracting spoil at a metered pace, keeping the face stable to within millimeters. On a strong week, a single machine advanced up to 100 meters, and by the time the drives finished, the 8 machines had removed roughly 7 million tons of excavated material from under the city. Not one recorded incident of ground settlement threatened a building above. Beneath the cutterhead runs the screw conveyor, a long rotating auger that is the real trick behind earth pressure balance boring. By controlling exactly how fast it turns, engineers control exactly how much soil leaves the chamber. Too fast, and the face loses support. Too slow, and thrust builds dangerously. Getting that balance right, meter by meter, is what let these machines pass under London's most sensitive structures, without anyone above ground feeling a thing. Slurry shield machines handle a different flavor of soft, wet ground, loose sand and gravel sitting under so much water pressure that even an earth pressure balance machine would struggle to hold the face. Instead of packing spoil into a chamber, a slurry shield pumps pressurized bentonite fluid against the cutterhead, then carries excavated material away as a liquid slurry through pipes back to a separation plant on the surface. The Netherlands built the Westerschelde tunnel this way between 1997 and 2003, boring 2 5.5-kilometer bores beneath the Westerschelde estuary to link Zeeuws-Vlaanderen to the rest of the country without a ferry crossing. The Westerschelde machine cut a face 11.3 meters across, one of the largest slurry shields built up to that point, working at depths where water pressure alone could reach 4 bar against the cutting face. Bentonite slurry pumped in at the face and pumped out at the surface plant carried excavated sand and clay away as a liquid instead of a solid, letting the machine keep boring even where the ground sat well below sea level and fully saturated with water. Advance rates settled around 12 meters a day through the 6-year project, respectable given that the entire drive ran beneath an active shipping estuary. When it broke through in 2002, the Westerschelde bore held the record for the deepest tunnel drilled beneath a Dutch waterway. The cutterhead alone rises taller than a 3-story building, an 11-meter disc of steel and cutting tools that would dwarf anyone standing at its base. Trailing behind it, the shield and backup gantry ran close to 130 meters, a rolling factory, pumping slurry in one direction and spoil in the other as it crept forward beneath the estuary floor. A Mixshield machine is a slurry shield with a second personality. It can switch between full slurry mode for soft, water-bearing ground and a simpler open mode for firmer rock, all without stopping to reconfigure. That flexibility mattered enormously on Hong Kong's Tuen Mun to Chek Lap Kok link, where the ground beneath the seabed shifted from soft marine mud to decomposed granite within a single drive. Herrenknecht built 4 Mixshield machines for the project, and between 2013 and 2015, 2 of them bored what became, at completion, among the widest subsea road tunnels ever drilled. Each Tuen Mun Mixshield cut a bore 17.6 meters across, wide enough for 3 lanes of traffic, stacked over another 3 lanes below, all inside a single circular tunnel. A submerged wall inside the cutting chamber let operators regulate air pressure independently of slurry pressure, holding the face steady even as ground conditions changed meter by meter. Rock crushers mounted just behind the cutterhead broke down boulders and hard granite chunks, too large for the slurry pipes to carry away, a feature open slurry shields don't need, but mixed shields can't do without in mixed ground. The drives advanced roughly 8 meters a day through some of the most variable geology any Hong Kong infrastructure project had faced, and the link opened to traffic in 2018. Just behind the cutting face sits the submerged wall, a steel partition that splits the working chamber in 2. Slurry fills the lower section against the ground, while a cushion of compressed air fills the space above it. By adjusting that air pressure independently, operators fine-tune how hard the face pushes back against the ground without touching the slurry pumps at all. It's the detail that let this machine handle mud and granite in the same afternoon. Herrenknecht designed the variable density machine for a very specific London problem: chalk riddled with flint, ground that behaves like solid rock one moment and loose rubble the next. Rather than choosing between an EPB and a slurry approach, this class switches its excavation chamber's consistency on the fly, running dense when the ground needs slurry-style support and open when it doesn't. 2 of these machines, named Helen and Amy, bored the Northern Line extension to Battersea between 2015 and 2017, threading new tube tunnels through exactly the kind of unpredictable ground that had troubled London tunnelers for over a century. Helen and Amy cut bores 6.2 meters across, modest next to the river-crossing giants earlier in this list, but built for precision rather than raw scale. Sensors fed real-time ground data back to the operators, who could shift the machine's working mode within a single ring of advance if the chalk suddenly gave way to a flint seam or a sand pocket. That adaptability let the machines average around 14 meters a day through ground that had stalled or damaged conventional TBMs on earlier London projects, and both drives finished essentially on schedule in 2016, delivering twin bores to a new underground station that opened to the public in 2021. Every class in this list has been building toward this one. Bertha was built by Hitachi Zosen for Seattle's State Route 99 tunnel, a project meant to replace an aging elevated highway with a bored tunnel running beneath the city's downtown waterfront. When it started digging in 2013, Bertha's cutterhead measured 57.5 feet across, making it the largest diameter tunnel boring machine ever put to work anywhere in the world, a title it still holds among large single-bore road tunnels. Bertha's cutterhead spanned 17.5 meters, wide enough to carry a double-deck highway, 2 lanes of traffic in each direction, inside a single circular bore instead of the twin tunnels a smaller machine would need. 25 electric motors turned that face with a combined output over 6,000 kilowatts, and thrust cylinders could push with more than 200,000 kilonewtons of force when conditions demanded it. Size brought a real setback, though. About 10 months into the drive, Bertha struck a buried steel pipe left over from an old groundwater monitoring well, overheated its main bearing seals, and sat stalled beneath the city for nearly 2 years while crews dug an 80-meter rescue shaft just to reach and repair it. Bertha finally broke through in 2017, 4 years and roughly $1.5 billion into a project originally budgeted for far less. Stand beside Bertha's cutterhead, and a person barely reaches above one of its lower cutting arms, the face alone rising higher than a 5-story building turned on its side. From the tip of the cutterhead to the back of its trailing support gantry, the full machine stretched over 300 feet, a mobile underground factory longer than a football field, including both end zones. Bertha's face carried 600 individual cutting tools, discs and scrapers arranged in sweeping spiral patterns, designed to chew through Seattle's mix of glacial till, sand, and buried debris. It was one of those tools' distant enemies, a stray 4-inch pipe far tougher than the till around it, that brought the whole machine to a stop in 2013 and turned a routine bore into the most expensive repair job in tunnel boring history.